Okay, as we have been going through this chapter, guys, we'll be doing evaluating of the properties, and I made the introductory remarks introducing the dome, the two-phase part, subcooled liquid, superheated vapor on the two sides of the dome. So let's just very quickly look at what we have been considering so far, and this is just okay, let me see. So this is that horrendous drawing that I tried to draw for you last time. Okay? And as you see, the most important part is the dome, liquid vapor part, the critical point, lines of constant temperature. If you follow these lines, of course, you see that it's a 3D case. But in a 2D-dimensional one, for example, in the pressure specific volume plot, I see a two-dimensional version of this. Okay? And then the lines of constant temperature are practically like this, as I showed the other time. So imagine if we have a PV plot with the dome. These are lines of constant T. Yes? Okay. So, and we are interested only in a PV plot or a TV plot. No, for the time being, yes.
Why do we not have solid vapor on the plot or the other way?
Because we are hardly dealing with solid in a thermodynamic cycle. Right? Mostly liquid and vapor. But of course, for other courses, that's of use a lot. Okay. Then, this is a 2D version of it. Yeah, of course. And I even drew some of these here. We are not interested in the solid, only liquid vapor, and therefore the part that we are interested in is practically this part here. And here on a temperature specific volume, I showed the lines of constant pressure are like this. Right? Okay. Now you are experts in PV and TV plots. Then, and these are all in the book. So, phase change, of course, we are talking about inside the dome. And I also showed actually this one. On a TV plot, imagine I have liquid water in this piston cylinder arrangement. We heat it. Therefore, at constant pressure, let's say atmospheric exposed on the outside of it. Therefore, it's always under atmospheric pressure. It goes from low temperature liquid to a boiling point first. 100 degrees Celsius. Then we start to form vapor. Volume increases. Therefore, I have now a mixture of liquid and vapor. And as you see, when all of it is vapor upon heating, you see that the specific volume at G much larger than the specific volume at F. Okay. And then we heat more, it goes into the superheated region, all at 1 atmosphere. This entire process. Okay. Similarly for cooling, it comes down this line and then goes into forming liquid all the way to the F point, and then if we even decrease the temperature more by cooling, it will go down along this line. Okay. This is the critical point line, of course, and then supercritical lines. There is no distinction anymore between liquid and vapor on the supercritical part. Okay. Same thing here. More discussion. Okay. Now, for the mixture, we define quality, X. X is mass of vapor divided by mass of liquid plus vapor, which means the total mass of the water in the cylinder. Okay? Therefore, at F, I have 0 vapor yet. Okay, so X is 0. By the time it reaches G, X has gone to 1. Let's say X 0.5, somewhere here maybe, on this line, if the pressure is atmospheric, outside. Any questions so far? Here, saturated vapor, as it says, X is equal to 1 because it's mass of vapor over mass of liquid plus vapor. No more liquid is left there. Therefore, M vapor over M vapor. All right. Then, superheated section. As you see here, in the superheated range, I need to know 2 properties still to identify the state. It can be temperature and specific volume, right? Or it can be temperature and pressure, right? The same point here, let's say point S, right now they call it. If I know the temperature and I know the pressure, I come here, the pressure is 1 bar approximately, 1 atmosphere. So I read, so this point, then if I need the specific volume, I come down and read the specific volume for that location, knowing the temperature and pressure. Okay? So that's for the superheated. Here, now let's see now, steam tables. One after another, these tables are, okay, table A2 through A5. Later look into it, and I'm going to show also how to use these tables. Notice that table A2 and A3 are for the 2-phase liquid vapor mixture. Okay? Now table A2, if I am not wrong, is based on the temperature. So let me show you here. And, maybe this should be actually the right level because you can see even better. But it's not here. Let me just turn all of them on. Okay. In the saturation table for water vapor, here we have the temperature listed, okay? In whole numbers, let's say in 20 Celsius, 40, 100, 200, 400, saturation, okay. Then the pressure is listed in front of the temperature, okay? For example, 1.004, 1.015, imagine. Okay, and these are in bar. You remember 1 bar 10 to the 5 Pascal, because 1 atmosphere is 101.3 kilopascal, equal to 1.013 times 10 to the 5 Pascal, right? That annoying 0.13, we are dropping it. 1 bar is just 10 to the 5 Pascal, and it's easier to show it like that. Okay? Easier to form the tables, as we will see in a minute. Then here we are showing VF and VG. Right? Meter cube per kilogram in the SI system. Okay? VF much smaller than VG. Orders of magnitude smaller, of course, because of the dome, as we see over there. Then UF, UG, internal energy is listed, and HF, HG, and sometimes enthalpy. I introduced enthalpy last time, right? H, you can see if I write here, H equal to U plus PV, yes? And therefore little h, little u plus pressure, get specific volume. Makes the job a lot easier when we look at the control volume analysis. Who has not taken MAE 101A? Okay, we will see later. Then okay, of course, 101A plus in MAE 11 are the prerequisites for 101B. Okay, but then we use the enthalpy H a lot in fluid mechanics also. And then sometimes HFG, which is Hg minus HF. Right? Heat of vaporization of water. Agree? HFG. I vaporize the amount of water by supplying HFG to the liquid in the piston. Okay. Units, sometimes joules per kilogram or not, or kilojoules per kilogram. I'm not sure which in the table, but let's say kilojoules per kilogram for both of these, for both H and U. And then entropy is listed, which we are going to cover later. So this is table A2, let's say. In this form. And of course, all of these values are listed. Therefore, if I know the temperature at saturation, which fixes my location here, right? Because I know the temperature and pressure is known because T and P are dependent to each other, on each other in this zone. That's why for each temperature you see a particular pressure, let's say. Okay? Imagine. These numbers, I'm making them up. But okay. So these two are dependent on each other. Similarly, you have table A3. And table A3, exact same things, but now based on the pressure. Here you have the pressure first, then the temperature, and then the U HFUG, HFFG, and SFSG, etc. Here then, the pressure is the whole number. For example, the 0.1 bar, 0.5, 1, let's say 2, 50, etc. Right? Then the temperature, for example, here is, I don't know, just picking up a number, 151.75. Right? Therefore, pressure is the whole number. If you are given the pressure, you can go directly to that table. If you are given the temperature, you can go to this table. All right. With this introduction, then later we look at the compressed liquid and the superheated tables as the. Should we continue with this slide? Is it okay? Now, this range I'm not too worried about. By the way, for each one of these tables, there is an English system also after this whole set of the SI tables. Then it's table A2E for the English system, then A3E, and etc. I'm going to show. So, now tables A4 and A5, and we are going to look at them soon, are tabulated as temperature, pressure, a specific volume, a specific internal energy, and a specific enthalpy. This I just wrote, H equal U plus PV. Okay. Enthalpy is also a property because each one of these three are properties. Agree? And therefore, we will see its significance later in chapter 4. And then a specific entropy, which is another intensive property. It's developed in chapter 6. We are going to look at it later. Okay. This is the example of a table A4. So A2, A3, you have seen actually this. Notice that because temperature and pressure in the superheat, because this is for a superheated water vapor, yes, as shown in red over there. In the superheat region, for example, PV or TV plot, lines of constant P. Here. Yes? Imagine I'm using a TV plot. Any superheated point, I must know temperature and pressure in order to identify the point. Therefore, you see in the table, okay, let's say temperature, right? 320, 400, 440. But pressure can change because at this temperature, right, at this level of temperature, let's say 440, these are lines of constant pressure. And so, which pressure are we talking about along that line? That's why these are sub-tables, I call them, P80 bar, P100 bar, P200 bar, 300 bar, etc. For each one of these then, listed is V, U, internal energy, enthalpy, and entropy. Okay, why? Because this is now a single point by itself, therefore no VG, no VF. Right? It's superheat. Just U, V, H. Okay. This line is the saturation line, reproduced from those tables. Okay? The saturation line at 80 bar is a fixed saturation line. Why? I'm jumping between these. Okay. This is a temperature plot, right? Or as a function of temperature. I have now pressures. Therefore, the saturation line for a temperature of 400 Celsius. Let's say this is 400 Celsius. Right? You can see in the back. Okay. This saturation line has its own pressure. Let's say P equal to, I don't know, 1.52 bar. Right? At 80 bar, saturation temperature, okay, at 80 bar, T saturation is 300. Let me correct it. So 295 something, right? 295 degrees, let's say, is here. This is my saturation line. Right? Therefore, at a temperature of 295, saturation line shows that pressure is 80 bar. For a pressure of 80 bar, saturation temperature is 295.7. For a pressure of 100 bar, the saturation temperature is 311. Okay, so 295 fixes 80 bar, 311 fixes 100 bar, 311 Celsius. Only this one is also given therefore as a, not as a reference, but as a information that we may need. And going back to that table, right, at a pressure of, this table, at a pressure of 80 bar, the temperature listed is 295 point something. So this is the beginning of this table, of course, because I am now starting from here and going in that direction. So for this 80 bar, this is the beginning of my table. Okay. Then 320, and as you see, always this temperature is less than the rest. Yes? Why? Because my plot, I made it too crowded. Because my plot starts okay. So looking at this, this was the temperature of 295.5 Celsius. Pressure 80 bar, dictated by this line. Agree? Because T and P here are dependent. Fine. But the start of this, as you see, for other pressures at P equal to 80 bar and all other higher temperatures, I can construct my table for V based on T. Very good. That's why I'm listing T. Therefore, P 80 bar, V U H S. Okay. Then 100 bar, T saturation, slightly higher, of course, as you see over there, and then V U H S. Yeah. Okay. Any question on this? You will get used to it. It's a little overwhelming at the beginning, I know. So, example, properties associated with superheated vapor at 10 megapascal, 400 Celsius. You have a piston cylinder, superheated vapor, 10 megapascal, 400 Celsius. You come here, 400. But what is 10 megapascal? As you see, it's 100 bar. Why? 1 bar is 10 to the 5 Pascal, or 0.1 megapascal. Therefore, the 10 megapascal is 100 bars. All right. 400 degrees, boom. The specific volume, meter cube per kilogram. The specific internal energy, 2,832.4 kilojoules per kilogram. The specific enthalpy, 3,096.5 kilojoules. Next entries in the table may be 200 bar, right? 400 bar, etc. Okay. So notice, superheated tables have, I call them sub-tables of their own, based on pressure. Any questions about this? No? I hope it's clear so far. Linear interpolation, you have done it in some course, I'm sure some interpolation. Okay? Sometimes things are not very clear cut. By that I mean, look at this. A state always does not fall exactly on the values that we have seen before. Let's say you are given a temperature of 411 Celsius at a pressure of 100 bar, right? You have to do interpolation. Okay. Let's look at this in a little more detail, because you may have to do a lot of interpolation in the next few weeks. When a state does not fall exactly on the grid of values provided by property tables, we do linear interpolation between adjacent entries. Example, a specific volume associated with superheated water vapor at 10 bar, 215 Celsius. Okay. Do we have 215 Celsius and 10 bar? No, we have 80 bar, 100 bar, right? But they have hopefully provided it here, yes. Okay, so this is the 10 bar, saturation temperature fine, saturation properties okay, but the temperature at 10 bar is 215 Celsius. You have 200 values, okay, great. You have 240 values, great. But what is it at 215? Let's look at this. Is this big enough from the back of the room, or shall I rewrite it on the blackboard? Is it okay? All right. Notice that at temperature of 200, specific volume is given 2060, 0.2060. At 240, we have also this value, but we don't have it at 215. Okay, so what do I do? You can use this. You can say, as I do mentally, this distance, let me show it better. Maybe this won't be even. Okay, this distance between 215 and 200 divided by the distance between 200 and 240 equal to this distance divided by this entire distance. Yes? All right. What you do, you can write 200 minus 215 divided by 200 minus 240, right? Equal to exact way that you did this one, you need to go here. 2060 minus V divided by 2060 minus 2275. And you solve for V. That's linear interpolation. So, just to make sure, because everybody can see this part here, so 200, 240, 215, 0.2060 for volume, 0.2060, the specific volume V and the temperature. And then the other one is 0.2275. 2275. What's your specific volume here? This distance divided by this distance equal to this distance divided by this distance. That's the graphical representation that they have shown. Yes?
Does this linear relationship exist between all the variables, or is it just temperature?
We do it between all variables. Right. We do linear interpolation in this course. If you want H, same thing, guys, right? Okay. Later, we want to do actually a double interpolation. Why is that? Because you can imagine here, fine, I have, let me grab this. Okay? Imagine you want to find the specific volume, right? At a temperature of 410 or 415, let's say. 415 and the pressure of 83 bars. Right? Or maybe even a bigger, 87 bars, let's say. Okay, what do? I do first interpolation in this table. Okay? Or you can start with this one. You need to do between we said 415. For 415, you must find this specific volume first. Yes? Then this specific volume here. Right? And then do interpolation between those two specific volumes for the pressure. Okay? That's called the double interpolation. Very good. If it's unclear, hopefully we will be able to do something here. All right. Two-phase liquid vapor region. This is the table that I showed here. No, tables A2 and A2E for the British system at the end of these tables. They are for temperature tables, and then A3 and A3E for pressure tables. Saturated liquid, saturated vapor. F and G data are given here, as I've just actually produced here. This is the temperature table. You see the temperature as the whole numbers. The pressure is given as whatever exact value of the pressure is along the two-phase line. Okay. Saturated liquid, what happened here? Okay. Saturated liquid, you see that, always in these tables you see, if you see VF times 10 to the 3, for example, yes? That means VF times 10 to the 3 is equal to this value. Therefore, VF is, for example, 1.0002 times 10 to the minus 3. Confirmation of that liquid has a much smaller volume than a vapor, right? Okay. So in any table, if you see right at the top, Vf times 10 to the 3 is, let's say, 1.201. That's, and then Vg has no 10 to the 3 or anything because it's big enough. Therefore, Vf, if Vf times 10 to the 3 is equal to 1.201, therefore Vf must be 1.201 times 10 to the minus 3. This is very important because I've seen a lot of actually mistakes the students make. Okay. Vg, according to this, is 2, for example, 206 versus 1.002 times 10 to the minus 3. Uf, Ug, as you see here, for saturated liquid, this is practically 0.01 has almost zero energy. That is our, let's say, reference point. Okay. Saturated liquid, saturated vapor for internal energy, little u. And then enthalpy, as I mentioned, enthalpy of evaporation, HFG. It's the difference between the G minus F. Heat of vaporization, practically. Okay. And then entropy, we worry about it later. To avoid any confusion, the first column and the last column are the same here. Right? So that you can go, if you are close to this side, you can use this part of it, right? Not to have to follow a line constantly. Okay. These equations I wrote at the end of the last lecture. For a two-phase liquid vapor case, I can find the quality X. I know that the total volume of the mixture, let's say I'm somewhere here, right, on this line. The total volume of the mixture is the sum of the volumes of the liquid and vapor in that piston, right? Therefore, V is V liquid plus V vapor. Divide by the total mass M inside the piston. Therefore, little v becomes V over M equal V liquid over M plus V vapor over M. Agree? From this, I know that V liquid is M liquid Vf. And V vapor total is M vapor Vg. Therefore, M vapor over M, we called it X. You agree? I call it M vapor over M liquid plus M vapor as X. But this is total M. Therefore, M vapor over M is X, M liquid over M, practically 1 minus X. Right? Substitution in that V gives me finally this one. I wrote these equations at the end of the last lecture. Okay, so you know how to find X from your volume and Vf and Vg, or knowing X you can find your specific volume from Vf and Vg. Similarly for H, similarly for U. Okay. So these three equations are practically the same, but for V, U, and H. Okay. pressure and temperature are not independent properties. They keep saying that because we must make sure that we really understand why and how we use these tables actually. Okay. Two-phase liquid vapor region. There is example. A system is a two-phase liquid vapor mixture of water at 6 Celsius. Quality of 0.4. Yes? So X is 0.4, T is 6 degrees Celsius. Determine the specific volume of the mixture. I know that V is Vf plus X Vg minus Vf. That was the back of this equation, right? Okay. So what do I need? I need Vf and I need Vg because I know X. Values from table 2, A2 they mean. Okay. First of all, at 6 degrees, we come to this table. Because the temperature is given, I go to table A2 because temperature is a whole number in that table. Go to 6 degrees, Vf, 1.0001 times 10 to the minus 3. Vg, 137.734. That's it. Substitute in this equation. With X, I get my V 55.094 meter cube per kilogram. Right? It's very scary, these tables, at the first, how to deal with them and everything. But when you look at it, it's just reading the values. Right? Because that is thermodynamics. Property data used in the closed system energy balance. Example. This is a good one. We have a piston cylinder that contains 2 kilograms of water at 100 Celsius. Okay? We know the mass, we know the temperature, and we know the pressure, 100 Celsius and 1 bar. Water is compressed to a saturated vapor state where the pressure is 2.5 bar. It helps for us to start from there and then with the diagram. We don't need this anymore, right? You have seen everything about it. Because I'm given the temperature and pressure, fine. Let's work with the TV plot. T, V, dome, line of constant P. P is 1 bar. Yes? Temperature 100 Celsius. That's when you boil water on the range. Okay. Then we have a pressure of, is it 2.5 bar? Yes. Very good. 2.5 bar. Okay. Now, the water is compressed to a saturated vapor state where the pressure is 2.5 bar. Okay. I have a piston cylinder. I have initially 2 kilogram of water in here. Fine. I now compress it to this state. Yes, same 2 kilogram. When I compress it, volume is decreased. Okay. And my end point is gonna be what? A saturated vapor, it says, yes? At 2.5. Therefore, I am here state 2. Saturated vapor at 2.5. Because I'm compressing, yes? Imagine we are, actually not imagine, we are actually setting this up from scratch. I'm compressing, therefore volume must decrease from here to here, right? Therefore I see that I must go from somewhere superheat in order to decrease the volume, because we are compressing to this end state. This is the volume here. This must be the specific volume somewhere. Clear what I'm doing, guys? Okay. Therefore, this process is not a very straightforward one. Why? Because somehow I go here like this, from state 1 to state 2, by compressing. Okay. Notice that you may say, okay, I may have two-phase, right? And I am compressing still. Or I can have saturated vapor, and I am compressing to saturated vapor. Who knows? Because everything is to the right of this line. Yes? All those 3 points that I'm saying. I can have superheat, I can have saturated vapor, or I can have two-phase and compress it to go to final state 2. Okay. But during compression, there is heat transfer of energy from water to its surroundings. Therefore, during this process, I have what? Q out. Okay. The amount of heat is 250 kilojoules. Q equal 250 kilojoules out here. In going from that state to this. At least we are given now some information. Neglect changes in kinetic and the potential energy. Determine the work in kilojoules for this process. Okay. This is now very clear, I hope. Yes? Heat is negative. Why? Going out. Right? Heat going in is positive, heat going out is negative. The equation for the energy conservation, you remember delta E equal to Q minus W, as in the book stated that, where E is what? Potential plus kinetic plus internal. Okay. It says neglect potential and kinetic energy. Therefore, here I have what? U2 minus U1 equal to Q minus the W. Right? Now Q going out, therefore I have negative 250 kilojoules. W, we keep it as a negative W. If this value is positive, it means work is going out. You remember the book saying that value positive with a negative sign, this work is going out. If the value of this W is negative, sorry, you can't see it over there with this one. Now, if this W is negative, that means work is going in. Okay. I haven't even seen the solution. Okay, this is the first time I'm looking at this chart after, I don't know how long. But look, energy equation, yes, I'm given heat, the heat, I need the work. What do I need? Internal energies, yes, between states 1 and 2. Okay, let's see how this is developed. So now remember, state 1, T1, 100 Celsius, P1, 1 bar. 100 Celsius, 1 bar. Okay, somewhere here we don't know yet. Right? And then final state we know, 2.5 bar. Saturated vapor. What do we have here in the, okay. Is this correct? Yes. Kinetic energy 0, potential energy 0, delta, because it's fixed actually. So, or whatever, delta is 0. Delta U equal Q minus W. Therefore, rearranging W equal to Q minus M U2 minus U. Therefore, for this equation, I see that the W equal to Q minus M little U2 minus little U1 from here. Let me erase this right now. Okay? Therefore, I need to find little U2 and U1 from the table. State 1, they say is in the superheated vapor region fixed by P1 1 bar T1 100 Celsius. Table A4, I don't have it here in front of me, but let me see if I, no, I need to get the tables uploaded. As a matter of fact, yes, we have them on the website, right? So give me a second, because this is going to be really helpful to see why it is superheated vapor. Okay. So give me 1 second. We have table A2 because I am given the temperature and the pressure. Yes? Let's go to 100 Celsius. See what is the pressure. Temperature 45. H2O, no. Okay, remember, for any material or for any substance, it's shown here. Okay? Later, ammonia or whatever, anything. 100 degrees. Pressure is what? 1.014. So remember that annoying 1.013. Okay, this is exact 1.014 bar. Why do I have superheated vapor?
It's larger than 1 bar.
Yes, let me just redo this so that it's very clear. Sometimes you have to justify it. Here I have 100 Celsius. This is the pressure line for 100 Celsius. Right? you see that in the saturated region, pressure is 1.014 bar. Therefore, this is P, 1.014 bar. 1.014 bar. Right? These are the lines of constant pressure, all of these. Okay? And I have said that pressure is increasing in this direction. Yes? Okay. So, if I am at 100 degrees and 1 bar, I see that 1 bar is going to fall maybe somewhere here with its own temperature at saturation. Definitely. Yes? As a result, if my pressure, if the temperature is 100 degrees, this will be my point 1. With the pressure of 1 bar and temperature 100 degrees. Anybody still having doubt? Now is the time. Okay? Therefore, my state 1 is superheated vapor. State 2, I have made these two close to each other, okay, but somehow I must go from here to here. Volume must decrease because I'm compressing. Okay, so this will be my process. From 1 to 2. Okay. Now back to this chart. From table A4, we are superheated vapor at pressure of 1 bar. Therefore, it's easier. No, let's go to the table and see. Let's go to the superheated tables. Going to the superheated tables. This is what? This is table A3, property saturated water, a pressure table. But I need superheat. Okay. Table A4 starts from here. Notice temperature based on a particular value of the pressure. Okay. 0.06 bar, 0.35, 0.71 bar. And the temperature is 100 degrees. Even this table gives you the confirmation of superheat because the saturation line values are given. Okay. 100 degrees, 1 bar. The specific volume 1.696 meter cube per kilogram. V1, let's just write it, all of them, 1.696 meter cube per kilogram. H1, U1, and then H1. U1, 2506.7. 2506.7. Don't round up. Okay, always keep whatever is in the table because sometimes it makes a big difference. A kilojoule per kilogram. Just being nosy, H1, 2676.2 kilojoule per kilogram. Okay. These are for state 1. Sorry guys, one of the TAs send me. Okay, I'm gonna call it. Okay, V1, U1, H1. Next. So we got U1 for the equation. State 2, saturated vapor at 2.5 bar. Going back, we go to the saturation tables again. Saturated vapor at 2.5 bar. This is the pressure, temperature table. Table A3 is the pressure table. 2.5 bar. Temperature is 127. Of course, why did I draw it from here to here? And nobody objected. Come on. This is 0.2. Where is my 2.5 bar? Here. Yes? Because this is 1.014 bar. This is 2.5 bar. Therefore, process is much more clear now. Okay. And U is therefore saturated vapor 2537.2. Yes? 2537.2. U2. Kilojoules per kilogram. I have U1. I have U2. 2537.2. Okay. 2506.7, 2537.2. And so the problem is solved. Substitute so. So W, negative 250 because heat is going out. Minus 2 kilogram times final minus initial states for U. Negative 311 kilojoules. What happens now? Does the work go in or go out? Go in. Because it is negative. Because this must be positive for work to go out. Work goes in is negative, the answer is negative, so is the problem statement is compressed. Work goes in. Very good. Okay, any questions here? So far, the steam tables, we are in good shape. Yes?
So when Q goes out, W has to go in, right?
Not necessarily. Sometimes we are not sure. Because why? Because U will be affected.
Oh, right.
Right?
Mm-hmm.
Yeah.
Yeah.
Accordingly, U will be affected.
But when the same U, like, the U doesn't change, then Q out and Q.
This is a good example for that. Okay. But again, what if it goes from here to here? Volume increases, yes? It gives me work. Right? Volume increases. A piston can push me in this direction, right? Therefore, it gives work out. That will be positive if it goes from a point here to a point here. Volume increases, therefore it gives work, therefore this is positive. Right?
And
it really depends on the process.
And when the volume like expands, then the Q goes in or goes out.
No, again it depends. It can go either way. Okay, why? Because I can have processes like this. I can have crazy processes, right? A combination, okay? You have to go one by one, make sure which is which, okay? So there is no specific rule. If heat goes in, therefore Q must go. No. You can have both added, both out, one out, one in, or the other way. Or even 1, 0, the other one going in, out, etc. Okay? As a matter of fact, one of the homework problems with the table, it shows you that. Okay. 613, let's look at, sorry guys. Next. Let me see before doing that. Okay, these are now pressure saturated ones. Let's go down this list. Superheated, all of these, right? Look at this, 0.7 bar, 1 bar, 1.5, 3 bars, right? The temperatures change because the higher the pressure, we must go to higher temperatures in the superheat range, basically. And so this table, it continues to, let's say 20 bar, 30 bar, you see the temperature has gone now to 700 level, okay, in that range. Then even more. Now, here is the superheat. Yes, 100 bar, 120 bar, 140 bar. Temperature has gone up to 740. And then 180 bar, then 200 bar, 240 bar. Let me make sure that this is not, yeah, it's still superheated. Yes. Okay, now $320 bar is very close to the critical point. Okay, that's why they have shown it as the superheated. Okay, why? Because right at the beginning, are these the critical points? No. Atomic molecular weights and critical properties of selected elements. Table A1. Very good. Yes. TCPC. Yes, for critical. ZC, we are going to look at it later. But for water, 220 megapascal. 220 bar is PC, the critical pressure. 647 is the critical temperature. Right at the nose here. Okay, but the superheated actually table. So this is right. This is 220 bar. But the tables, superheat tables, give you even more. Right? Up to 320. Why not? Okay. Next. And so, then there is, I want to show you the compressed liquid case, because that will be enough for today. We have 3 minutes left. So, compressed liquid water. Let's pay a little attention to this. Look at this. It starts from 25 bar, 2.5 megapascal, 50 bar. Let's see if this is, yeah. Table A5. 25, 50, 75, 100, and etc. Notice that here V times 10 to the 3 again. Yes, because it's liquid. And then based on these, why? Because now in this section, and one very important thing I want to mention before we adjourn, because this caused me to get this single thing caused me to get a B in my thermodynamics in undergrad years. Otherwise I would get an A. Okay, I made a mistake in the final exam. Look at this. And I haven't forgotten it after so many years. And many students make a mistake in the final exam because of that. T versus V. Yes? Dome. Lines of constant, now pressure. P. Okay. Subcooled liquid. Here. This table that you see is for this section. Okay? Knowing the temperature, for example. What do you have? Knowing the temperature and the particular pressure, you can find your values for V, U, H, and everything. Here. Let's see. I know the temperature, I know the pressure, I go to the table. I may have to interpolate sometimes. But let's say the temperature is here. And I don't want to use this table. Why? Because water is not too receptive to compression, right? Liquid. Volume hardly changes. Internal energy is only function of temperature in general, as we are going to see later, okay? And enthalpy. So, if you don't want to use this table, or if you don't have table for ammonia, methane, anything subcooled liquid, they don't usually provide the table for. Properties, let's say I want to find the property at point A, right? U, V, H, all at point A, approximately equal to U, V, H of saturated liquid at the given T, not P. So what you are doing, you go straight here, you read the saturated liquid, you are home. Okay? Because everything practically, V is not a function of the temperature much for liquids, right? Therefore, V is practically the constant. Therefore, okay? So everything, H, U, everything is a function of temperature. The saturated liquid at the same, can be equal to the saturated liquid value at the same T. And I'm gonna explain that again.